Hello students, welcome to Akshara 8 Foundation. So today we will continue the last topic. We are discussing about the moment of inertia. So moment of inertia for regular shaped bodies we are finding there. So we have found in the last class the moment of inertia about the line joining the moment of inertia of a uniform rod about the line passing through the center of the uniform rod. So for that we have found there. So today we are going to see the moment of inertia of the ring about the axis plane perpendicular to its plane. Okay. So the moment of inertia the moment of inertia of a ring about an axis passing through center plane perpendicular passing through center perpendicular to its plane. Center perpendicular to its plane. Perpendicular to its plane. So moment of inertia of a ring about an axis passing through the center and perpendicular to its plane there. Perpendicular to its plane. Perpendicular to its plane there. Suppose let us consider this is a circle, a ring, and ring means the mass has present only at the edge. So at the periphery of the body, it is like a bangle there. Okay. So now the mass will present at the periphery of the ring. So now the center of mass will be here there. Now it is rotating about this. It is rotating about this axis there, and about the axis plane perpendicular to its axis. Okay. So now suppose if you consider this is a ring there, about this axis it is rotating there. About this axis plane perpendicularly, the plane of ring is perpendicularly, it is rotating. So this is okay. So now about this axis it is rotating there. So then how to find out there? So we have here. So for that we will consider a mass dm mass of the body. So let us consider this is a dm mass of the body, and this dm mass of the body is at a distance of let us consider it is r there. It is r. Okay. So now the moment of inertia of that will get there. No. So I is equals to r. We can add there di is equals to, we will get here moment of inertia. So this is a mass, not dx it is. This will be the mass. So we write here dm, mass of this ring there. Mass of the ring we should consider, and this mass of the ring is, it is continuous up to here, no, means this is suppose if we consider 0 to 360 degrees, 2 pi we can add there. So integral of 2 pi. So here we can add there 0 to, so what can we add there? This is a perpendicular distance, this is a radius r. So now here moment of inertia, mass, product of mass and the square of the perpendicular distance there. So we can add here product of mass. So dm we can add dm into r square we can add here. So that can be written as here di is equals to, we can add here r square into dm we can add. So now if you do integration on both sides, both sides, so we will get there. So here whenever it is rotating when we are rotating in anti-clockwise direction or clockwise direction, so the radius will be constant, the bangle radius, I mean perpendicular distance from this particle of mass about this axis it is constant, no, mass will be constant there. So here integral of di will get there, here I is equals to This r is constant, it can be taken out common, so dm we can add there. So from where it is moving there, from it is started from 0 to here, we can add there in one circle, in one rotation. In one rotation, what can we add there? 0 to pi. So 0 to pi we can add there, no? So integral of 0 to pi. So here integral of dm. So integral of dm, what is there here? So there is no other term, no? Integral of dm will get there here m only. So therefore m is I is equals to here r square into integral of m is nothing but we will get here dm. So m will get there m. So now here I is equals to m r square. I is equals to m r square will be the moment of inertia of the ring about an axis passing through its center perpendicular to its plane. Okay, the moment of inertia of a ring about an axis passing through its center, passing through the center and perpendicular to its plane. The moment of inertia is, we can write here m r square. Moment of inertia will be m r square for a ring. Okay, so now next one we are going to see there. The moment of inertia of a uniform circular plate about its axis there. Okay, the moment of inertia of circular plate, okay, about its axis there, about the axis, means about the axis and plane perpendicular to its center, same like that. So now here we will consider there, next one, the moment of inertia, the moment of inertia, the moment of inertia of a circular plate, the moment of inertia of circular plate about an axis, passing through its center, about an axis passing through its center and perpendicular to its plane, perpendicular to its plane there, perpendicular to its plane. Perpendicular to its plane. Now the circular plate. So circular plate we will consider like this. Circular plate means throughout this area of this plate, the mass will be present there. So now it is rotating about this axis. So this is the center, about this it is rotating there. So now we will consider the mass. Okay. So how can I consider the mass there? So dm mass, here let us consider this is the dm mass of the body about this axis. So about this axis of rotation, we will consider a small amount of mass which is rotating. Okay. So here we will consider the small amount of dm mass is rotating about this axis. So this we consider the dm mass, and that mass will be, it is at a distance, perpendicular distance we can write here. This is a perpendicular distance from the axis of rotation. So it is the perpendicular distance, we can write like this. This is r perpendicular distance. R will be the perpendicular distance we can write. Okay. So we will take here mass per unit length, mass per unit area, dm. So we'll consider there about this axis it is rotating, no? About that axis, and here this r and dm mass of the body if you consider there, and it is spreading from the center, from here to from the center to the circumference of the circular plate. Okay, so the mass will be spread from here to the radius of the circumference. Suppose if it is taken here, this is a r distance. Here we'll consider there r. R will be the perpendicular distance and mass, dm mass if it is considered there. And the dm mass is, and here this dm mass will be dx radius. This dm mass will be considered, it is there about this axis. The distance is about, it is a dx distance. So this will be the dx distance, we'll consider dx distance. Now we should consider there mass per unit area. Mass per unit area. So if we consider the mass of the circular plate is capital M, okay, and area of the circular plate, area of the circle, we know that. So we can write here that is a mass per surface density. So we can write here sigma is equals to mass per unit area. Mass per unit area. So here m divided by pi r square. M divided by pi r square we can write there. Okay. So area of the circular plate. So we can write here mass of the body, mass of the circular plate is capital M and area of the circular plate is pi r square we can write there. Pi r square. Okay. So now this one, this is equal to here we can write there mass. This small m mass, okay, this dm, differential mass divided by, so differential here area, differential area, this one here dx into, what is the radius here? The radius we have taken here distance, let us consider here it is x distance, okay. So this distance we consider there, it is a x distance, and radius of the circular plate we consider there r, small r, okay. So now here small m, mass per unit area we can write here this radius into dx. So means here we can write there x into dx we can write there, x into dx, that is the area, means x into dx we can write there, and x into dx, and here throughout this dx, it is there throughout this circumference of a circle there. So 2 pi x into 2 pi r we can write. No, generally the circumference of a circle 2 pi r we can write there. No, so here now we can write there. So this dx into 2 pi r we can write there, so that it can be cover the total area of the circle. So here we can write there this one 2 pi x into dx, 2 pi x into dx. So dm by 2 pi x into dx we can add there. So now we should find out here dm value. Okay. So how to find out dm value there? So dm is equals to you bring this side here 2 pi x into dx, 2 pi x into dx divided by here divided by, so m into here m divided by pi r square, m divided by pi r square we can write there, m divided by pi r square. Okay. So now this pi and pi will be cancelled. So here dm is equals to, we will get there 2 into capital M x into dx, x into dx divided by r square, x into dx divided by r square will get there. Okay. So now we should write here moment of inertia. Moment of inertia about this total. So dm mass we found here. So now the moment of inertia, it can be written as here di is equals to, so here distance we can write here x square into here we can write there dm. So dm, x square into dm. Here the dm mass is at a distance of x from the axis of rotation. Okay, then we can write there moment of inertia of that small moment of inertia, differential moment of inertia, it can be written as here di is equals to x square into dm we can write there. Now if you do integration on both sides, we will get there I is equals to integral of di is equals to I. So here integral of x square into dm will get there. So what is the dm value we got here? That value we should write here. So this one, to 2 pi by r square into x into dx, 2 pi by r square into x into dx we can write there. So we write here, so integral of x square into, so 2m x into dx divided by 2m x into dx divided by r square. So this is a r square. Okay. Now r square is common here. 2m will be common and r square will be common. So we will get here I is equals to integral of, so 2 into capital M divided by r square x cube into dx, we can add there, x cube into dx, x cube into dx there. So now here the distance, this x cube is what, from 0 to r, no? It is moving from 0 to r. So x is moving from, means we are moving from the center to the radius of the circular plate. So radius of the circular plate is here r, so small r we have written there. So now from this we can write I is equals to, so now this 2m by r square is a common there, it can be taken out from the integration 2m by r square, integral of 0 to small r into x cube into dx, we can add there, x cube into dx. Okay. So now here I is equals to 2m divided by r square. So this one here x power 3 plus 1 divided by 3 plus 1, integral of x power n dx. Integral of x power n dx formula is x power n plus 1 divided by n plus 1. So here we can add there 0 to r, limits we should write here now. So then I is equals to, from this I is equals to, so 2m by r square. So here x power 4 divided by 4 will be there, and this is here 0 to r. Now, so we should substitute their upper limit and lower limit. So now from this I is equals to, so 2m by r square, here r power 4 divided by 4 minus here 0 power 4 divided by 4 will get. So now from this I is equals to, so 2m by r square into here r power 4 divided by 4 will be there, r power 4 divided by 4. So now what happens here now, this is I is equals to 2m into r power 4 divided by r square into 4 will be there. Now here square, r square and here r square will be cancelled there. So here 2 remain there, and 2 and 2 and the 2 2s. So now we will get there. Therefore I is equals to moment of inertia of the disc about an axis passing through its center. Okay, it is mr square by 2 will be there. So this is a moment of inertia of the disc. So by using this formula we can find out the moment of inertia about any axis. Okay. Now we are going to find out the moment of inertia of the spherical shell. Moment of inertia of the spherical shell. Hollow sphere. Spherical shell is nothing but hollow sphere. So the moment of inertia of the circular plate. The circular plate is also called as a disc. The moment of inertia of a disc about an axis passing through its center and perpendicular to its plane is moment of inertia is equals to mr square by 2. Mr square by 2. It's clear now here? So you need to understand this one here actually. Surface density we can add there. So in the while we are finding the moment of inertia of a uniform rod about axis perpendicular to its plane. So there we have taken their linear mass density. Okay, linear density. Okay, so linear mass density we have taken here, and here we are taking it is the circular plate, so or the disc. So that disc will be, in the disc it is the mass is distributed throughout its area. So then we should consider here area, mass per unit area, surface density, mass per surface density. Okay, So surface density, mass per unit area we can write there. Mass of the capital M will be the mass of the capital M will be mass of the circular plate, and here R will be the radius of the circular plate, or circular disc. Then here x and dx. So x will be the dm mass. We consider the differential mass. We consider there. The differential mass is considered throughout its circumference of the circular plate. The circumference of the circular plate, we have taken a distance dx. Distance dx. A small amount of mass it is considered there. So around the axis of rotation in the circular plate, the total mass it is considered there. That small distance of the dm mass is dx, and that it is at a distance of from the axis of rotation x distance. So now here we'll write there. So differential mass. So now here mass per unit area is nothing but mass of the circular plate by area of the circular plate. So m by pi r square will get here, and here dm by, here we should write the dm. So differential mass divided by, and so area covered by this differential mass about this axis of rotation about which it is rotating. Okay. So now here dm by, so how to write there? This dm mass is completing a circumference of a circle about the axis of rotation. So here the circumference of circle, what can write there here? So generally 2 pi r means length into breadth we can write now. So that is here 2 pi r will be the total distance covered by the this mass, and that mass is how much distance here? How much distance it is there? Like we can consider that it is a breadth. So length into breadth is nothing but area will get, no? So in the same way here 2 pi x into dx we can add there. So differential mass and differential area covered by that differential mass of the body. That is, so from that equation we will get the dm mass. From this dm mass can be written as here, you send do the cross multiplication, 2 pi x into dx will get there, here into m by pi r square will get there. Now pi and pi will be cancelled, so remaining value 2 capital M by r square into x dx will be there. So now we know that to find out the continuous mass distribution of the bodies, the moment of inertia of the continuous mass distribution of the bodies can be used by the formula is this, no, integral of di is equals to, so x square dm. So x square dm here we can add that. So x means this dm is at a distance of x. We have seen there here, no? This dm mass is at a distance of x. So we write here that x square into dm we can add there. Now dm value what we got here? So 2 capital M. So here also we should write there, this is a capital M, no? Here you continue, this is a capital M only. So this is a capital M only. Here final answer also capital M. So capital M. This is a capital M only. So dm value we got here from this equation, from the previous equation, 2m by r square x into dx we can add there. So here we'll write there 2m x divided by r square into dx we can add there. So now this 2m by r square is a constant there. So mass of the circular plate is constant and radius of the circular plate is constant there. It can be taken, 2 is also constant, so it can be taken out from the integration. So remaining is what there, and this mass is varying from where? From, it is varying from the 0 to radius of the circular plate. So it is 0 to radius. So 0 to r we can add there. Okay. So now 2m by r square integral of 0 to r into here x square into x, it will become x cube. And we know the formula, integral of x power n dx, that formula will apply here. Integral of x power n dx is nothing but x power n plus 1 divided by n plus 1. So we will write here x power 3 plus 1 divided by 3 plus 1. Limits are here 0 to r. So now we will get there I is equals to 2m by r square. So x power 4 by 4 will get there. Now lower limit and upper limit we should substitute there. So first we should substitute the upper limit minus the lower limit. So upper limit is r, in place of x we should substitute there r there. So if you substitute there r power 4 divided by 4, 0 power 4 divided by 4 will be there. 0 power 4 means 0 only will get there. So we will get here 2 capital M into 2 capital M divided by r square into r power 4 by 4 will be there. If we simplify there, we will get I is equals to mr square by 2. Mr square by 2. That is the moment of inertia of the circular plate about an axis passing through its center and perpendicular to its plane. perpendicular to its plane. So now we will find out moment of inertia. So we will find out moment of inertia of a thin spherical hollow sphere, spherical shell, otherwise we can say thin spherical shell, we will say that. Okay. So next one, right on there. It's clear now?